And so if the number of turns is too large, no, it's not too large. Number of turns, maybe, suppose it's too large. And you may say if the number of turns are too many, okay. So the length of solenoid will be always large. Clear? Like this. So we have connected it with a battery. So as we will connect it with battery, there will be current, right? So if there is current passing through in these loops, so there will be magnetic fields. So yes, in this loop, there will be magnetic field, this loop, this loop, this loop. There are n number of loops, a lot of loops, so there will be magnetic field. So there will be magnetic field in between the loops. If the solenoid is too large, so there will be magnetic field in between the solenoids. So the direction of magnetic field will be same as the direction of magnetic field due to a bar magnet, right? The North Pole and South Pole. This will be like this. North to south. And inside will be like this. So this will be the same as the bar magnet. Clear?
Yes, sir.
So if you want
Sir,
to
can you explain again? I didn't understand.
Okay. So we know that if we have a circular loop, a single loop, and current is flowing through that loop is I, so there will be a magnetic field. Clear?
Yeah, yes, sir.
If there is a straight wire, then also there will be a magnetic field circling around that wire. Okay. So suppose now we have arranged n number of circular loops and we have connected it with a wire. So if current is passing through it, so there will be magnetic field due to one circular loop. Similarly for the next circular loop and the next one. Okay. So there are n number of circular loops tightly wound wire. So there will be a magnetic field throughout this conductor, right? This will work in the same way as a bar magnet. Okay, so suppose this is a bar magnet and we have magnetic field from north to south. Clear? In this, it will act in the same way. Clear?
Yes, sir.
Okay. So it's time to check what will be the magnetic field in all these three cases. Due to a straight wire, circular wire, or a solenoid. Actually, I checked some question papers and I found that there were some numerical questions. The relation of magnetic field directly, no derivation, because derivation is a part of undergrad course. So in those standard questions or some coaching institute questions, they have asked the value of magnetic field due to all these three setup. So now I'm going to write first point, magnetic field, due to a straight wire. Straight wire, or you may say that magnetic field due to a long straight wire. Okay. The current flowing through it is current flowing is capital I at a point R. So what does it mean? We have a long wire passing the current I and we have to find the magnetic field at point R. Clear? So magnetic field, we write it a capital B. We write it as a capital B. So B at point P, we will be right. B due to a strong straight wire is mu naught. This is constant I divided by 2 pi R, where mu naught is constant. And we also know that pi is what? 3.142. This is also constant. Clear? Constant.
Yeah, yes, sir.
Okay. There is we already know what is the current, because the current is being for through what can I say, flowing in wire, passing through the wire, and we know the position of this point from the wire. Clear?
Yes, sir.
So now we will, this is only the results. Okay, we don't, you may write or take the screenshot. And see, this magnetic field is a vector quantity, is a vector quantity. Vector quantity. Vector quantity means it has direction and magnitude as well. Clear? This is the, we have only written this magnitude. We didn't have make it the vector. So this is only the magnitude. Clear?
Yes, sir.
Okay. So see, it depends on 1 over R, or directly proportional to the current. So we may write that summarize B is directly proportional to I, given R is constant. Given R is constant. If R is constant, so B is directly proportional to R. Or B is inversely proportional to the separation or position given I is constant. Clear?
Yes, sir.
So now I'll ask you one question. The question is, we have a conducting wire, and current I is passing through it. And we have position A, this is R, A, and we have another position B, that is R, B. So will you tell me magnetic field at point A, dot, 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 magnetic field at point B. And you have to fill it with less than, greater than, and equal to. Question is clear? Question is clear or not?
Yes, sir.
Jaslyn, question is clear? So now tell me which sign you will give, a smaller, greater, or equal.
Um,
Sorry? Do you have answer?
Sir, is it smaller?
It is a smaller. BA is a smaller. Now, see, this is inverse relation. B is inverse to R. It means when R is a small, B will be large. When R is a small, B is large, right?
Yes, sir.
So at BA, the position is small, so B will be larger. At B, the RB is larger in compared to RA, so field will be smaller. So I think what will be the answer?
La-
Hmm? What
Larger.
will larger? Rizwan, what will be the answer?
The large.
Yeah, so it will be large. So we are only writing the magnitude. We didn't written the vector, right? So this is only magnitude. Will you tell me what will be the direction of both or any? You already calculated the direction when current is going upward. If you guys remember, we did this. Recall.
Sir, can you say again?
Hmm?
Can you say again?
Okay, I'm asking that use the right hand thumb rule and tell me what will be the direction of magnetic field for BA or BB,
Left side.
left side. So I will hold like this. So this side it is coming and this side it is going inside, right? This side it will be coming up out of paper. This side it is going inside the paper. That's it, na?
Yes, sir.
Right hand thumb rule. If you are confused, then go back and check the video or read the book. So it's clear. Should we move further?
Yes, sir.
Yes,
So
sir.
you have written it.
Yes, sir.
Okay, so now I'm going to remove it. Unfortunately, I don't have much space. So now the question will be changing like that. I will change the question. Now the question is magnetic field due to a circular loop, a single circular loop, not the solenoid one. Magnetic field, that is B, and due to a polar ring, or it is ring that's ring, so right, no need to write it, circular ring of radius r, comma, current I. Clear? So it means that we have a circular loop of radius r and current is I. So we're going to find the magnetic field at O. So B at center is equal to mu naught I over 2R. Clear? So if you have to find the magnetic field at the center of circle where current is I, you will just put these value. That's it. Where we know that mu is constant and I is the current. That's it. See over here. Here it is also B is inversely proportional to R. If the circle is large, at its center there will be less magnetic field. Or circle is smaller, then at the center there will be large magnetic field. We are talking about center, not out of center. We are concentrated at center. Magnetic field B due to a current I at center. Clear?
Yes, sir.
Okay.
Yes, sir.
So now move on to write it down or take the screenshot.
That's all right.
Okay, so now we have the solenoid one for a solenoid. Magnetic field for a solenoid. Field due to a long solenoid of length L, okay, radius R, and number of turn and total number of turn, total number of turn N. So it is like for this solenoid, okay? Figure is this. So where we have to find at the center, at the center. So B is simply mu naught N I, where N is total number of turn, and further we will write mu naught N I, where mu naught N I, right directly this. Okay. So where N is total number of turn per unit length. Clear? Where N is total number of turn per unit length. Clear?
Yes, sir.
Okay. So now we will be moving to the next concept that says that if we have a current carrying wire, suppose this is a current carrying wire. So when the current will pass through it, it will produce a magnetic field and we bring another magnet. Okay. So as the current will pass, there will be deflections. Clear? If current is not passing, then this is the aluminum metal, suppose, and we have a horse type magnet. So when we will keep, there will be no deflection. As the current will pass, there will be deflection. So it is says that this statement, okay, this is statement. So this is a metallic wire and this is a magnet. So direction of magnetic field will be from north to south. Direction of B will be north to south, and here the direction is current. Direction of current is in this direction. So direction of magnetic field is upside. Direction of current is in this side. Suppose this is what? Coordinate geometry. X, Y, and Z. X, Y, Z. Okay. So if current is flowing in this direction, or magnetic field is in direction, then force will be in this direction, right? So like left hand Fleming left hand rule, it's being called. So suppose magnetic field is in this direction and current is in this direction. So the force will be in this direction. Clear? So hold on. If it is not clear, I'm going to show you a short video. So hold on. First stopping the share, new share. Where is it? Where it is, right? Are you visible to see the YouTube channel screen?
Yes, sir.
So it video says something in Hindi. We don't have to worry about that. But it is
से आगे की ओर, पीछे से आगे की ओर.
the direction of current,
मैग्नेटिक फील्ड
north to
नॉर्थ
south,
से साउथ की तरफ,
downward.
ऊपर से नीचे की तरफ. तो इंडिकेटर फिंगर मैग्नेटिक फील्ड को रिप्रेजेंट करेगी ऊपर से नीचे की तरफ. इस सेटअप के अकॉर्डिंग फोर्स की डायरेक्शन होनी चाहिए राइट हैंड साइड की तरफ. तो अगर हम इस सेटअप में स्विच ऑन करेंगे तो फ्लेमिंग लेफ्ट हैंड रूल के अकॉर्डिंग वायर में डिफ्लेक्शन राइट हैंड साइड की तरफ होना चाहिए. एक बार ऑन करके देखते हैं. ऑफ करके फिर ऑन करते हैं. तो हम देख सकते हैं.
Did you understand?
Yes, sir.
Okay, so this was a bit demonstration of Fleming left hand rule. Okay, so remember to find the direction of magnetic field in a straight wire, we were using the right hand rule, and to calculate measure the direction of force or a current carrying conductor, we will be using left hand rule. Clear? So now it's time to Jaslyn, you understand it or not?
Yes, sir.
Completely? This is the
Yes, sir.
mutual effect of both current carrying wire and the magnet. So it is mutual effects. You may say that electricity and magnetism are mutual to each other. Now back to our own discussion. So if you understand the concept, you may write it in your own words. Can you do that? Jaslyn and Rizwan, can you do that?
Yes, sir. But this the left hand rule, right, sir?
Yeah, this is left hand rule, Fleming left
Okay.
hand. And I will explain it bit. There are a few more points to explain. You will see if NCRT that given the pictorial representation, and I think that will be fine. That will be fine. I forget to put that photo. This is the left hand rule, Fleming's pictorial representation. Once you are done, let me know.
So done.
Okay. So it's better if you draw the figure as well, okay? Because it may ask in some short notes or long notes. So it's better to. So actually, this is the key. This is the introduction. We already learned that current flowing through a conductor produces a magnetic field. This is well established discovery. The field so produced exert a force on magnet placed in the victini of conductor. We saw that in the compass needle, when compass needle is being brought near to a current carrying conductor, the needle was getting deflected. We got from there. So till now, this is okay. A French scientist, Ampere, suggests that the magnets must also exert an equal and opposite force on the current carrying conductor. Newton's third law is over here. If the current carrying wire deflecting the magnetic needle, so that magnetic needle should also exert equal and opposite force on the current carrying conductor. That was the effect over there. Clear? Did you get it? You read the book, and I think in each line there is a number of informations. So please go and read the text. This is a small extract of it. Now, we saw in that video that magnetic field was, let me draw if you remember. This will be the over here. Anyone remember what was the magnetic field? In that case, magnetic field was like this, right? That example video, the direction of magnetic field was like this. Okay. And the direction of electric field was like, direction of current was like this, coming out of the paper. Remember? So we saw that force was in this direction. Here, the direction of magnetic field is like this, and the direction of current is same. Direction of current is coming out of paper. So force will be in this direction. So it means that this is north and this is south. In that case, this was south, this was north, and this was south. So one observation is that if we will change the direction of magnetic field, if we change the direction of magnetic field B. Okay, so what will change? Tell me what will change? The direction of force. Force will change. Force F will change. Clear?
Yes, sir.
Now, if we change the direction of current, what will happen? And we are keeping the direction of magnetic field intact. If we are changing the direction of current, what will happen? What will happen to the direction of force?
It will also change.
Yeah, the force will also change. Either you change the direction of magnetic field or the direction of current. It will result in a change in the direction of force. Clear? Any doubt?
No, sir.
So write this point as well. Second point. If we change the direction of current, keeping magnetic field intact, right? F will change. Clear?
Yes, sir.
This was the Fleming right hand rule. And we will be using these concepts in electric generator, electric motor, loudspeaker, microphone. This all works on the same principle. So uses electric motor, generator, loudspeaker, and the microphones etc. Clear?
Yes, sir.
Any doubt?
No, sir.
So if no doubt, then no doubt. So I think next topic is electric motor. So we don't have time. It will take almost one class to understand the principle and working all. So one more concept is induction. Induction. induction cooker as well. Okay, same, it's coming induction. Suppose this is a metal. Okay, like that. If I say in another way, if this is a loop, okay, and we connect this loop with a galvanometer, galvanometer, gal V A no METR meter, and this is a magnet. If we will bring magnet inside this loop, this is north and this is south, and just make it to and fro. Just make it to and fro. So what will you observe in the galvanometer? Galvanometer is a device that is being used to check the deflection or the generation of current in the circuit, right? So we have a galvanometer and a solenoid, and we have to just bring the magnet inside. Bringing the magnet inside means that we will be changing the flux. So when the flux is being changed, what will happen to the galvanometer? Do you have any guess? Do you have any guess what will happen?
No, sir.
So if current is flowing through a conductor, we bring a magnet get motions or get
Hmm.
deflected. Now what I am doing, I am keeping the conducting wire without any electricity. I'm not passing the electricity. I'm doing the inverse phenomena. Now we are deflecting the magnets inside the loop. That's just the
Current
reverse
generated.
phenomena. The current will be get generated. That's called the induction effect. Okay, okay. That's
Yes.
being termed as electromagnetic induction. So I think every term, so if you think, you may write it down the definitions. Clear?
Yes, sir.
Any doubt? Any questions?
No, sir.
No, sir.
Everything is okay.
Yes.
Okay, so make the notes proper in a proper way. If you have any doubt, are you guys reading the NCERT textbook?
Yes, sir.
Jaslyn, do you read NCERT textbook or whatever you have the reference book?
Yes, sir.
So do you understand everything or not?
Sir, up to now, yeah.
Okay, so try to read the books again and again. Okay, from there you will get the concepts. Because in 10th standard you have to study a lot because there are a lot of concepts. So these were the class for today. Next day we will start electric motor. Clear? Electric motor works on the change of flux. Okay, that electric fan you see now, that's also work on the change in flux. The wire is being wounded on a circular plate. So that's plate, there is two, secondary and primary. So we'll discuss. If we'll only see in the words or in the sentences, you won't understand. We have to see the working of it. Okay. So we'll see it tomorrow in the next class, hopefully. Let me see if we could complete any of the question, magnetism in medicine. So there are a number of application of that medical sciences as well. Okay. Magnetic field is being used in our medicine or medical professions. Can you name any? Can you name any a device that's being used in medical professions or treatment?
Yeah, any what, sir?
Do you know that magnetism is being used in medicine as
Yeah.
well? So
In
have, like MRI, have you heard about?
Sir.
yes, I heard.
So what is MRI? Can you write a short notes on that?
I don't know.
Right.
But I heard.
Yeah. So write a short notes on MRI. Write a short note on MRI, magnetic resonance, or something is like magnetic resonance induction. There we use magnetic field, high magnetic field, like sometime 4 Tesla, 3 Tesla. That's why when you enter in the MRI room, you are advised to remove your metallic objects like
Yes,
belt or
sir.
something,
Yeah.
because it has high magnetic field. If you will go with some metals, then metal will be attracted by that machine and that may damage that. Okay. So that's why we are being advised to remove. Where you see that advice, Jaslyn? Have you
Sir,
been there?
yes, sir.
Okay. So how was your experience?
Um, it's not supposed to be close to machine. Only the patient is supposed to be close.
Uh,
That they're going through the machine like a door,
uh,
like a door.
okay. Actually, your voice is not good. It's lagging, or what can you say? That's not continuous. So try to fix your mic. So this is the magnetic resonance imaging. So this is one of the use. Either you read this paragraph or make a short notes, because science and technology is helping in our day-to-day life. These are improving our lifestyles. Okay. So that maglev train as well. Have you heard about the maglev train? Maglev, magnetic levitation. It's work in China, Japan, maglev train. So that's
Trains, right?
also work on the magnetic field, right?
Yes, sir.
So do Google and make at least 5 or 10 discoveries, list it, and try to put it on the classroom noteboards, right? So do this if you are interested, but I will encourage you to Google these things and come up with ideas, right?
Okay.
Okay, then now we will be ending today's class. Okay.